300 feet below the surface of the Pacific Ocean, something enormous is on the move. It's invisible from a boat. It doesn't show up on satellite photos of clouds or storms. But buoy sensors scattered across the equator are tracking it in real time. A wall of warm water roughly the size of the continental United States, sliding slowly east beneath the waves. Scientists call it a Kelvin wave. And the last few times one this large appeared, it didn't just warm the ocean. It triggered floods in Peru, droughts in Australia, crop failures across 3 continents, and economic losses measured in the trillions of dollars. NOAA has just issued an El Niño watch. Some of the same forecast models that predicted previous Super El Niños months in advance are now flashing a warning that 2026 could produce one of the strongest events ever measured. Not might. Could, and the data behind that word is worth understanding before the headlines catch up, because by the time this shows up on the evening news, the fishing fleets and farmers who depend on the Pacific will have already felt it. Here's the uncomfortable part. El Niño isn't new. It's been cycling through the Pacific for thousands of years, and meteorologists have been tracking it formally since the 1960s. So why does a repeating climate pattern still have the power to catch entire countries off guard? Because El Niño doesn't behave the same way twice. Every event is shaped by the ocean conditions, the wind patterns, and increasingly, the background warming of the planet it's unfolding on top of. The tools scientists use to even measure El Niño were just updated in 2026, because the old ones were starting to give misleading answers in a warmer world. Understanding what's forming in the Pacific right now means understanding how this system actually works, where it came from, and why the 3 strongest El Niños in recorded history left such a long trail of destruction. Under normal conditions, the tropical Pacific runs like a conveyor belt. Trade winds blow steadily from east to west, piling up warm surface water near Indonesia and the western Pacific. As that warm water gets pushed away from South America, cold, nutrient-rich water rises up from the deep to replace it, a process called upwelling. That cold water feeds enormous fisheries off the coast of Peru and keeps the eastern Pacific relatively cool. El Niño begins when those trade winds weaken. Without the wind holding it in place, the warm water that had been stacked up in the west starts sliding back east, exactly like the wave currently crossing the Pacific. As that warm water spreads eastward, it suppresses the upwelling that normally cools the coast of South America. The ocean surface warms further, and here's the part that turns a minor wobble into a global event. Warmer water reduces the difference in air pressure between the eastern and western Pacific, which weakens the trade winds even more. Weaker winds let more warm water flow east. More warm water weakens the winds further. This self-reinforcing loop is called the Bjerknes feedback, and it's the engine that can turn a modest warm patch into a basin-wide El Niño, capable of shifting weather patterns on every continent. It's worth pausing on why this feedback loop is so unusual. Most systems on Earth resist change. Push on them, and something pushes back to restore balance. The Bjerknes feedback does the opposite. Once it starts, each part of the system makes the next part stronger, not weaker. Warmer water weakens the wind, and weaker wind allows more warm water through. That's why El Niño doesn't ramp up gradually and predictably like a thermostat. It can sit quiet for months, and then accelerate rapidly once the loop fully engages, which is exactly the phase scientists are watching for right now. Long before satellites or ocean buoys, Peruvian fishermen noticed the pattern first. Every few years, around Christmas time, the cold, fish-rich waters off their coast would suddenly turn warm, and the fish would vanish. They named the phenomenon El Niño, the boy, after the Christ child, because of when it arrived. For centuries, it stayed a regional mystery. That changed in the early 20th century, when a British scientist named Gilbert Walker, tasked with predicting Indian monsoon failures, noticed something strange in barometric pressure readings. When air pressure rose over the eastern Pacific, it tended to fall over the western Pacific and Indonesia, and vice versa, a seesaw pattern he called the Southern Oscillation. Walker couldn't fully explain why it happened, but he proved that the atmosphere over the Pacific was behaving as one connected system. The missing piece came decades later from Norwegian-American meteorologist Jacob Bjerknes. In the 1960s, Bjerknes connected Walker's atmospheric seesaw to the ocean-warming Peruvian fishermen had described for generations. He showed that the ocean and the atmosphere weren't separate puzzles. They were locked together in a single feedback loop, each one driving the other. That unified system now carries his name in spirit, and is known today as ENSO, El Niño-Southern Oscillation. It took 3 separate discoveries, made decades apart, on different continents, to fully explain a pattern that Peruvian fishermen had simply lived with for generations. That's often how science works. Not one breakthrough, but a slow assembly of pieces, until the full picture finally clicks into place. To track ENSO, scientists rely on the Oceanic Niño Index, or ONI, a 3-month running average of sea surface temperatures in a stretch of the central Pacific. When that average rises ½ degree Celsius above the historical norm for 5 consecutive overlapping seasons, NOAA officially declares an El Niño. But that index has a growing problem. The historical norm it's measured against was set decades ago, and the entire Pacific has warmed since then. A temperature anomaly that once signaled a major El Niño might now just reflect a slightly warmer baseline ocean. In 2026, NOAA addressed this by rolling out the Relative Oceanic Niño Index, or RONI, which adjusts for that long-term warming trend, so that today's El Niños can be compared more fairly against events from 40 or 50 years ago. It's a quiet but significant shift, proof that even the rulers we use to measure climate have to evolve as the climate does. Only 3 El Niño events in the modern record have been powerful enough to earn the label super. The first arrived in 1982 and 1983, catching forecasters almost completely by surprise. It triggered torrential flooding across Peru and Ecuador, devastating drought in Australia and Indonesia, and widespread coral bleaching across the Pacific. Global damages were estimated in the tens of billions of dollars. The second came in 1997 and 1998, and remains one of the most studied climate events in history. It pushed global temperatures to then record highs, fueled catastrophic flooding in East Africa, intensified drought across Southeast Asia, and contributed to wildfires that burned across Indonesia for months. Estimates put the global death toll in the tens of thousands and economic losses well over $30 billion. The third, in 2015 and 2016, unfolded on a planet that was already warmer than it had been during the previous 2 events, which amplified its impact. It drove one of the most severe global coral bleaching events ever recorded, deepened drought across southern Africa to the point of triggering food crises, and combined with background warming to make 2016 the hottest year on record at the time. Each of these events followed the same basic physics, but each one hit a different planet, with different baseline temperatures, different populations, and different vulnerabilities. That's the pattern worth paying attention to heading into 2026. El Niño doesn't stay in the Pacific. Through what scientists call atmospheric teleconnections, the heat released by a warm tropical ocean shifts the position of jet streams and rainfall belts thousands of miles away, rewriting weather patterns across the entire planet. Southern Africa, Indonesia, and Australia tend to dry out, often facing severe drought and an elevated wildfire risk. Peru and East Africa typically see the opposite: intense rainfall and flooding. The Indian monsoon, which hundreds of millions of people depend on for agriculture, often weakens significantly during strong El Niño years. Disrupted rainfall and flooding also create ideal conditions for disease outbreaks, with cholera and malaria cases historically spiking in El Niño years across vulnerable regions. And in the Atlantic, the very same atmospheric shift that dries out Australia tends to increase wind shear over the tropical Atlantic, which is part of why strong El Niño years often bring quieter hurricane seasons for the United States and the Caribbean. One ocean current. Measurable effects on 6 continents, which is part of why El Niño is one of the few climate phenomena that economists, public health officials, and farmers all watch as closely as meteorologists do. So where does that leave the wave currently crossing the Pacific right now? The ocean signals are real. Sea surface temperatures in the central Pacific are running well above average. The Kelvin wave is propagating exactly as the Bjerknes feedback would predict, and NOAA's confidence that El Niño conditions will persist through the coming winter is high. But ocean warming alone doesn't guarantee a Super El Niño. The atmosphere has to cooperate too. The trade winds need to keep weakening, and the feedback loop needs to fully engage rather than stall out partway. Some forecasting models are already projecting that this event could rival or exceed 1997 and 2015 in strength. Other scientists are urging caution, for a simple reason: climate change has altered the baseline ocean temperatures, wind patterns, and atmospheric moisture that ENSO operates within, which means the historical playbook may not translate cleanly to 2026. In other words, humanity may be watching one of the most powerful natural climate cycles on the planet unfold on a version of Earth it has never operated on before, using a measurement tool, RONI, that didn't even exist a year ago. Both the climate and the instruments built to understand it have changed at the same time, and over the next several months, that combination will be tested in real time on every continent simultaneously. If you want to actually track this event as it develops instead of waiting for the headlines, subscribe now, because the ocean data behind this video updates weekly, and the early signals are usually months ahead of the news coverage. Drop a comment with the region you're watching most closely, whether that's drought, flooding, or hurricane season, and I'll be covering the next update as soon as NOAA's models shift. And if this kind of science actually being explained, instead of just reported, is useful to you, there's a lot more of it waiting in this channel right now.